mathematical physics has been delivering, which includes a lot of this kind of what string theorists do, has been delivering diminishing returns for a few decades.
If you're going to do this, if you're going to not have experiment telling you whether you're right or wrong, it's very easy to fool yourself.
I agree with Peter, but then I disagree.
We just see that question very differently.
This is an unprecedented conversation. Today we have Peter Woit from Columbia University, known for his trenchant critique of string theory in Not Even Wrong, both the book and the blog, and Joseph Conlin from Oxford University, author of Why String Theory and a radiant defender of string theory. This remarkable and forthright exchange covers the technical ins and outs of a theory that's dominated fundamental physics for the past few decades in a manner that's never been seen before in podcast form. Both agree that the field of fundamental physics faces structural problems in how it trains new generations and evaluates competing ideas. Yet they diverge drastically on whether the problems string theory solves are indeed problems it solves, whether it's as elegant as people suggest, and whether its unparalleled mathematical divination, foreshadowing, for instance, mirror symmetry and modularity of partition functions, actually signals that string theory is on the right track or a seductive dead end. Many in the public jump on the string theory bandwagon, either being for it or against it without knowing the details of what they're supporting or criticizing. That's why it's thrilling to bring this conversation to you. My name is Kurt Jaimungal, and on this channel I research mathematical physics and philosophy in front of you in podcast form, bridging these disparate subjects and making abstruse concepts digestible while not skimping on, nor being afraid of, the technicalities. If you're a graduate student and want a flyby overview of string theory, I have a 3-hour compendious iceberg covering its mathematical details, link in the description. Welcome to the podcast, Joseph Conlin, Peter Woit. Joseph, you're known in the popular sphere as a sharp defender of string theory, and Peter, you're known as a sharp critic of string theory. Joseph, you have a book called Why String Theory from 2015, and Origins, the Cosmos in Verse from a month ago, 2024. And Peter, you have a book called Not Even Wrong from, remind me of the year?
It was published in 2006, I guess. It was written a couple years earlier.
And both of those are on screen and the link are in the description. I recommend you check it out, especially the Why String Theory book as it's relevant to this conversation and Not Even Wrong. Although for a more poetic excursion into these topics, Origins, the Cosmos in Verses is relevant. Now, many people are watching this expecting, perhaps even hoping for disputatious and entertaining bickering. Now, I'm less interested in that, as you know. If you watch this channel, I'm more interested in how can we productively move theoretical physics forward with congenial, generative, technical exchanges. After going through both of your work, I found several lines of convergence, so how about I pose some of those questions first, and then we can get into your respective defenses and critiques of string theory.
Okay, sure.
That's also good. Yeah.
All right. What aspects of the standard model do you find to be most ad hoc and unsatisfying? And we'll start with you, Joseph.
So I think, let me split those into what's kind of seems sort of definitely needing explanation and things where we also think there's kind of experimental chance in the near future. So things like the Yukawa couplings of the standard model, for example, the fact, the electron Yukawa coupling is 10 to the minus 6, there's clear, 3 families and you've got roughly a kind of a order of magnitude or so, or 2 orders of magnitude or so between them in terms of masses. So that's clearly structure not explained by the standard model, and we need something more. But the thing which I think where there is most experimental chance to do something in the near future is that of what's called the strong CP problem. And this is an angle that's present in the Lagrangian of the standard model in the strong force sector. And it's equivalent to the question of whether the neutron, which is electrically neutral, whether this has an electric dipole moment. And this appears to be zero. I think the general view, which I also subscribe to, is the best explanation for this would be that the angle is dynamical. And in this case, this leads to a particle called the axion, which could possibly be a part of dark matter. And there is a lot of intense experimental work covering, kind of trying to think about how you would look for the axion in the various different regimes or masses and couplings it could have.
Okay, well, it's hard to say. I think the first thing to say, of course, about the standard model is that what's most amazing about it is how good it is, how successful it is. So I think my point of view is different than many of people's, that I think it's actually something much closer to a final theory that really is perfectly satisfactory than what many people think. The things that there are some basic facts about it, some basic aspects of it that really kind of cry out for some kind of explanation for where did that come from. I mean, one is the pattern of gauge groups and of representations of gauge groups describing the matter particles, the forces between them. It's kind of a frustratingly kind of simple kind of structure, geometric structure, but with no explanation. Then, of course, as Joe mentioned, there being the Yukawas, what's causing, and the whole general story of the Higgs. There's clearly something about the Higgs sector that we don't understand where this is coming from. Most of the kind of undetermined numbers that go into the standard model come from the Higgs sector, come from the couplings to the Higgs. So that's the thing that we kind of is most crying out for some kind of understanding. I guess if I had wanted to point to something, and I think there's some hope of getting some experimental evidence about in the reasonable future, I'd point more to the neutrino sector. That's a very funny story, and the story about neutrino masses and the story about a possible right-handed neutrino field is something, again, it looks like where there's something we don't understand and something going on, and possibly it's something we actually have some hope of getting experimental evidence about. About the axion, I guess I'm less fond of the idea that that's dynamical. I think it may be the reason that term is zero may just have something more to do with our incomplete understanding of the quantum field theory that governs that.
So the other ideas with the axion have been, for example, there's an idea that because it's equivalent to, you could tie it to relations in terms of the quark set, you could move things slightly about. So one of the things has always been that there's the intrinsic Yukawa of, I think, the up quark is zero, and that there's no, and then in that case the axion ceases to be dynamic. There ceases to be a kind of a physical field, and you can solve the strong CP problem because you can tie it to the phase of the quark sector, and there is no physical phase if the actual Yukawa is zero. I think lattice results tend to disfavor this explanation. And so, to me, the axion it's one of these things which is kind of theoretically simple, explains the required phenomenon, and so to me, my kind of judgment call is that this is something like the Higgs was prior to its discovery. It's the sort of simplest and most minimal way of explaining the strong CP problem of the standard model, and you can't say it's 100% guaranteed that there definitely will be an axion, but to me it seems by far the most appealing and most likely explanation compared to the other possibilities.
Yeah, I just think I see things somewhat differently, partly because I think, unlike you, I don't see a good candidate for a dynamical field for where that would come from. It seems to be an extra structure. Actually, my original work in this field, when I was a graduate student, I was working on lattice gauge theory calculations of topological charge, and actually very specifically the whole, in some sense, this was supposed to be a calculation of the theta dependence in pure QCD. And I don't know, I guess it's been a long time since I've thought really seriously about this, but I kind of left that subject feeling, that there were kind of fundamental things about the whole story that we didn't really understand. These arguments about theta dependence kind of make various assumptions about, for instance, they only make sense really in Euclidean space-time. They make various assumptions about quantum field theory, which are quite plausible, and it's quite understandable. You should accept them, but it's also quite possible that there's something we're missing there. One of my fellow students at Princeton at the time was a very brilliant physicist named Hidanaga Yamagishi, who unfortunately died relatively early in life. But he was always strongly of the opinion, that there was a fundamental misunderstanding going on of the theta dependence problem and of this whole story. And not long before he died, he sent me some short papers he'd written about this. And anyway, I think there's at least some chance that the explanation is that he's right, or that some version of that we're missing something about this, because it's a bit trickier, I think, than people really actually realize.
I mean, ultimately, the answer is going to be experimental. The good thing about, I think, with axion searches is there's a very active experimental program. There's a sort of a canonical line. You can do this sort of plot of kind of axion mass against coupling for the kind of the canonical values where the axion would be expected to solve the strong CP problem. And I think it's generally true that things are not there, but that but there's a kind of there is a developed experimental program that is looking to just kind of bring down the couplings for which you can search for axions, with the aims of either discovering or excluding the axion across this range of parameter space. And so I think ultimately what's going to happen is this parameter space is going to be covered, and then either the axion will be discovered, or if it's not discovered, then I think it'd be reasonable to say then the question of is the axion the solution of the strong CP problem? We would then say, well, if it hasn't been discovered, why not? But ultimately, there's going to be an experimental answer to this, and I think it's also likely to be an experimental answer to this in the next kind of 10, 20 years, hopefully shorter. But there's a very active experimental program about looking for axions across a whole wide range of masses and couplings. This is something I have worked on myself as well.
So, Joe, people know you also because of your one-page paper. What is the direct experimental evidence of string theory, of which there's a single line, and everyone's jealous that you were able to publish with just a tweet, and it says, there is none, something like that.
Yeah, so that's actually in the book. That's in Why String Theory. So, the books are like a 230-page book or something, which is designed as an intellectual kind of explanation of and defense of kind of string theory as why so many people work on it, and why, in my view, it's kind of such an intellectually solid and interesting thing to work on. But then one of the chapters is called Direct Experimental Evidence for String Theory, and this is the one page chapter. And if you take this in the context of the book, you will see that what then follows in the next chapter is the question of, well, if there is no direct experimental evidence for string theory, which is true, there is no direct experimental evidence for string theory, and it's important to be honest to the public and say that, because that's true. Then one can, and I think one does, give this reason for why do so many people work on this, given that this is not something like QCD or something where you can say there is abundant experimental evidence that this is absolutely the correct theory of nature.
So, going through your work, Joe, I found 4 different critiques that you consider to be invalid. I found some critiques that you do consider to be valid. I'll talk about the misguided ones first. People will demand direct experimental evidence at the Planck scale as a prerequisite for taking string theory seriously. You don't think that's terribly valid. People dismiss string theory based on criticisms from people who have little to no expertise in the field, and they probably don't know what Ricci flatness is or what that has to do with string theory, so that's to be dismissed. And then there's an overstating of the significance of the landscape problem without acknowledging that there are ongoing efforts to address it. And that, I guess this is a defense, that string theory is like the opposite of fossil fuels, because you get these positive externalities where you provide tools and mathematical insights. So let me know if I summarize that correctly, and then feel free to expand. And then, Peter, I would like to hear your thoughts.
Let me come to some of these. So first of all, quantum gravity intrinsically, if you want to talk about things that go beyond the standard model, go beyond general relativity. So the number of people in the world with a technical understanding of things like quantum field theory or general relativity is kind of a relatively small fraction of the population. The fraction of the population who seem to have strong views on string theory and whether or not string theory is a correct theory of quantum gravity seems to be a lot higher than the fraction who have some sort of technical knowledge of say quantum field theory or general relativity. And so I think it is a bit odd to me that there seem to be far more people invested in the notion of what is the correct approach to quantum gravity than have, on any reasonable level, an ability to form a technical judgment about any of the issues relevant to it. I'm sure Peter agrees with this because it's just...
Yeah. Undeniably, I agree completely. Actually, I did want to actually say, it's hard to kind of overemphasize that these are complicated topics, and I do think Joe's Why String Theory book is the best and serious kind of defense about this, and addressing a lot of the issues that I brought up. So I find it, I think a lot of first advice to everybody who wants a kind of a serious understanding these issues is, read his book. I think he actually did an excellent job of doing it, much better than anywhere else. At the same time, you should also read my blog and my book, and you'll get a different point of view. But it's hard to overemphasize how complex a lot of these issues are. I mean, these discussions that people are conducting on most ridiculously on places like Twitter are kind of absurd, given the actual complexity and intricacy of the issues involved. And they're and Joe, he's perfectly right. They're mostly carried on by people who have no idea what they're talking about. So it's
Okay. So how about we get to the Brian Greene question? What grade do you respectively give to string theory? And we'll start with you, Joe, then we'll get to Peter, and then we'll have this exchange of lob some vitriolic aspersions. As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts, from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe. Lob some vitriolic aspersions.
Okay, so I'll give it an A+ because you want me to give it an A+, and then Peter can give it an E-, and then we can have some verbal.
An F. I don't know.
Yeah. Okay. A grade for what? So, if, like I said, there's no. Yeah. I mean, a grade as a theoretical structure, something I think likely to be true. Definitely A. A grade for something we know is part of nature. We know is empirically is true. Well, then currently it's certainly not a passing grade because we don't know that it's part of nature. But I'll give it an A+ because you want me to give it an
A+. Well, there's largely three families or like particles. Number one, string theory as a physical theory. Number two, string theory as a production of mathematical insights as well as physical insights, but outside string theory. And number three, string theory as a sociological phenomenon with its concomitant hype.
Yeah.
So how about a different grade set for each of these?
Okay, so if you want, string theory on a timescale of kind of 200 or 300 years, so this is the question: is string theory a true theory of nature? So I'm going to say I think it is. Okay, high grade. String theory, where it's something where, as happened in, say, the Standard Model, happened in particle physics in the 1960s, 1970s, where you have this very close interplay between theory and experiment, and the two drive each other forward. So on the kind of 5-10 year timescales, well, let's give it a D or an E because clearly that's not happening. The kind of question of sociology or string theorists, I mean, whether everything is optimally structured to create progress in the subject. I'll give it a C.
Okay, yeah. So I guess starting with the, I think that the first one is where I mainly disagree with Joe. I don't think. I mean, everything I've seen about string theory. I mean, I understand why people. I understand why it's an attractive idea and why some people find it have found it that way and believe that that sooner or later this is going to turn out to be the right way of doing it. Everything I've seen is kind of the opposite. I just think that this is an idea which the more you look at it, you find that this is it's just not working. It's not doing what you want to need. So that's where I think we have the strongest disagreement. And I'm not sure what grade that corresponds to, but a very low one. On the question of what's been going on in string theory research and what it positive and negative, I think. they're there again. We're starting to get into this very serious issue that it's very, very hard to actually know what you're at this point when you say string theory, what you're talking about. If you're talking about very specifically the proposal for a unified theory based upon starting with a 10-dimensional superstring and doing compactification, that's a specific proposal, and that I think is one that's not going to work out. But now when you talk about string theory, you can mean is AdS-CFT string theory? There's a new paper by Witten and a collaborator this morning about JT gravity in 2 dimensions. Is that string theory? I mean, it's actually very hard to kind of give any kind of evaluation of what string theory as currently practiced by most string theorists is, because it's impossible to actually tell who's a string theorist and what string theory is. And that's part of that ties into a sociological problem that I'm interested to see that Joe's grade is relatively low. I think, I think it's hard to deny that there actually has been a serious problem with how this has been practiced as a field of science in terms of, and it's a difficult problem. How do you evaluate and conduct research on a subject which is so difficult to get any experimental evidence about? And there's a lot of what I was writing about in the book and what I've often written about has been, the problems that this causes, and we can talk more about those, I think. But again, it's a very complicated subject, and a lot of the problems are also driven by the lack of kind of better alternatives of people not, of people. I think an alternative of a lot of people is that, well, I'm not very happy with how things are going or what's going on now, but I don't see anything better to do, and that's a large part of what's going on.
Let me pick up on the thing of which I think is absolutely true, what Peter says about the question of what's meant by a string theorist, or because there is this has become highly amorphous. In the sense, it's almost the case that what is meant by string theory is the research done by certain kind of prominent researchers at places like the IAS or Harvard or Stanford, and it's obviously true that the actual connection to, for example, quantized strings on the world sheet, or something that very clearly involves strings, as in one-dimensional extended objects, can often be rather nebulous. And so I think this is certainly, and lots of people have observed this. If you look at the strings conference, the actual topics that people might talk about, there may be rather small number of kind of strings there. And so this is certainly true that often when people are talking about string theory, it's a really much more nebulous idea, which is almost like a certain community, which is around a certain number of people. And the actual topic, the actual research we're actually talking about is not. And one thing it certainly isn't, which I think often gets people in the public get completely wrong. What it isn't is the idea of string theory as a fundamental theory of nature that is sitting behind the standard model as the kind of the deep structure of the standard model, the deep structure of this universe. For good or ill. I think mostly ill, but lots of people think for good. I mean, most of the research that is in string theory is kind of much more in the sort of mathematical physics area, with kind of very tangential at best connections to the physics of this world.
So then, Joe, what is the definition of string theory? It's whatever is practiced by the people who are at least previously called string theorists?
In some ways, that's how, when people use the term, you can, of course, and I would, when we distinguish between string theory and string theorists, I would give a very strong defense of, there is this theory that you develop from starting from quantizing one-dimensional relativistic strings. And this then leads you to theory of strings, and this has led to a lot of these things like holography, AdS-CFT, lots of dualities. There's a lot of this stuff which very clearly fits into this framework. And that intellectual structure, I will absolutely 100% give this an A grade, and you ask me to bet, I will say this intellectual structure really does sit underneath at the smaller scales. But it's clear, obviously, that a lot of papers people write, a lot of what the people in the community do, does not necessarily fit into that. And so I'm afraid it is a slightly nebulous term. And yeah, that's the word we're living in.
Now, Joe, ADS-CFT and holography aren't exclusive to string theory, despite them being birthed by it. So is the argument that they're just best developed, best articulated in string theory? Is that sufficient in your eyes to plant the string theory flag on the holography continent?
I think the best developed examples of holography are those where there really is a tie to string theory, like the ADS5 cross S5. This is the original one connecting to n equals 4 super Yang-Mills and the physics of D3. This really is string theory. The idea of holography does exist in a way that does not rely on string theory, but in my view, all the kind of really most solid and really fully worked out examples are all in string theory.
So what do you say to that, Peter?
Well, I think, so ADS-CFT, again, is a very, very complex subject to say something about. I agree with Joe that, the connection to string theory and the kind of, being able to say something more than kind of general things about, vague things about holography is in this ADS5 case, in the 5-dimensional case. And your problem is that doesn't, the problem with that is that doesn't connect very well to the real world, either in being at, we live in, not in 5 space-time dimensions, but in 4. And, and the hope that there's always been a very different hope for that I think motivates some of that research, which is that you're going to be able to solve QCD using that. And that there's technical reasons why that hasn't worked out so well. But I think that ADS-CFT was 1997, so that was 27 years ago, and so it's kind of became. This is actually something I didn't really say much about in the book, because the book was largely written in the first few years of the 2000s when the ADS-CFT was just starting to get going, and it wasn't clear at that point how much it was going to dominate the subject and the whole a large part of the subject, and I think it has, and there's a lot of interesting to say about that. I think one thing that really struck me actually this morning waking up, as I do, I often look and see what new papers there are on the archive, and I kind of mentioned this earlier. One paper that appeared today, there's like a 60-some pages written by Ed Witten and Jeff Pennington, which is a lot of very, very technical stuff, and actually, a huge amount of kind of work and intellectual power and has gone into this work clearly. But what it is, I think, is a thing that it's an example of something that's been a major theme, in string theory as practiced by people at the IAS or very influential people, especially in the subject, which is to address the fact that there's a lot. The whole idea of this ADS-CFT duality, there's a lot missing there. You don't really understand exactly what this means or exactly what's going on. So you want to kind of find some simpler case where you really could get control of it and really use it and really understand exactly what's happening. So you start. One thing you do is you go to lower dimensions, and one thing you do is you look at ADS3 CFT2, where you really have a lot of control of you'll know a lot more about the CFTs, and you hope to be able to kind of say something about 3-dimensional gravity. And then if you look at what's happened in that subject, that's turned out just to be very complex, and how gauge gravity duality is supposed to work even in this lower dimensional case is quite tricky and turns out to be very complicated. And people spend a lot of time going even farther down and going down to 2, to basically, to 2 and 1 dimensions and to this JT gravity. And so there you can calculate all sorts of things, and you can apply, there's all sorts of things you do, but if you want to make this look like, instead of having a nice, simple, beautiful picture about here's how this works, it becomes very complicated and very, very tricky to get this to do what you want. So, on the one hand, Witten and very influential people have spent a lot of their life now down in these very low dimensional toy models trying to get some handle on what's really going on there. And I don't think that's, to my mind, that hasn't been much of a success. At the same time, I also saw online, Witten is giving a talk, opening a conference in Turkey today, and he's giving a talk he's often given about, what every physicist should know about string theory.
Uh-huh.
And that talk is, very much a promotional effort. It's completely, that I actually have very serious problems with. I mean, you can look up various versions of his talk, and he's a genius. He's very smart, but he's making a very he's giving a certain technical reason for a whole kind of ideology, which I really don't think works out very well. And at the same time that he's still doing this and trying to promote this idea and trying to, part of it is, I guess, defense against critics like me. At the same time, if you look at what he's actually doing, he's been going down a bit of a rabbit hole of where ADS-CFT has led to. And, there's all sorts of interesting things down that rabbit hole, but they don't really look like what you want.
One thing I will pick up on, which I think maybe I broadly agree with Peter on it, is that sometimes if you look at sometimes things like the Strings Conference, which is this, sometimes they have these kind of public talks, and then you look at what's been put in the public talk, and it will be something like, you start with the standard model. We need to get the physics of the standard model. We need to do the physics of gravity, string theory, fundamental theory of nature. And the justifications that is kind of presented in that for string theory is the sort of, basically we're doing particle physics and we are trying to get the smallest things of nature. And then you actually look at what all the technical talks on the conference are, and they're all on kind of physics in 2 dimensions or 6 dimensions or 3 dimensions or, any number of dimensions other than 4. With n equals 2 symmetry, when you Thor supersymmetry, so that all the actual research that they, then is most elevated is actually nothing to do with these kind of particle physics questions. And so this, I do agree that the case, whatever the case you would make for something like detailed studies of holography in n equals 2 or JT gravity or anything like that, this case is not really a case. This is not what we are trying to do. Is we are trying to understand the laws of this universe, and we are trying to kind of go beyond the standard model, which often is the case that is made in public talks.
Peter, you said that you had several criticisms of the talk by Witten, at least, I don't know if it's the most recent one, but some of the ones in the past, what every physicist should know about string theory. What is one specific technical issue that you have with one of those talks, because there are several and they've changed across the years, that you think would be most interesting to discuss here?
Oh, I was just looking at it again this morning, trying to think about what to discuss here. And so anybody can look at this. So he actually started doing this, I think, in 2015. There was a version of it that appeared in the Physics Today, and he started giving many talks. And I think at the time, I've now kind of forgotten. I think I wrote about it in the blog and tried to kind of go through this carefully and address seriously what this was. But I think I was just looking at this again this morning. So I'm trying to understand Witten's point of view, and I think what he there's some very technical issues. I mean, one thing is he kind of tries to motivate this by starting out with not quantum field theory, but kind of the path integral quantization. We're saying we're going to have a particle theory and we're going to sum over paths. And then if you try and put in interactions, then you have to decide what's going to happen when paths join. And this, you can think of this as a little bit of a caricature of where the problems of renormalizability come from the short distance behavior. And then he says, well, then in strings, instead of having these paths, you have world sheets, and the world sheets don't have the same, they don't have interactions aren't introduced by what's happening at intersections of paths. So, so you're not going to have that problem. But it's kind of, It's kind of avoiding the main issues. I mean, because the what he's talking about is actually a single particle theory, and that's actually not what we do. I mean, that's actually not what quantum field theory is. Quantum field theory is a theory of fields. Interactions come from these have a geometrical origin and gauge symmetries and stuff. They're not. So he's kind of giving a really unfair caricature or characterizing quantum field theory in a way which I think is really doesn't have much to do with the real thing and the real problems of the thing, and then trying to to use that as justification. Well, world sheets are going to solve our problems, and I don't. Anyway, so that's kind of just a beginning of a technical argument against it. It is interesting. I was looking at a more recent version of this that he gave, and it's clear that I think when he's confronted about this, I mean he's making a bit the case that Joe is making, that there's clearly something very interesting going on here, and I think the way he likes to say it is that it's very, very hard to find any kind of consistent thing which goes beyond quantum field theory, which is not a quantum field theory, but which generalizes quantum field theory and still satisfies the fundamental principles you need to satisfy, and that the fact that string theory exists and is such a thing, makes it highly worth studying. This is certainly true. It's the problem again is that people have been doing this for a long time. I mean, he first proposed the idea of M theory in 1995, so now nearly 30 years ago. There's something very complicated and interesting going on there, and with S dualities relating theories in unexpected ways, and but the kind of idea that there is some kind of well-defined fundamental, in some sense, simple, basic structure, which is behind all this, and which is going to actually be useful for describing the real world. I just don't see. I don't see the last 30 years as being very kind of kind to that idea.
Joseph, what do you broadly agree with and disagree with?
Yeah, there's a view among a lot of string theorists. This is kind of string theorists, the community that would go something like this. So this is a view I don't actually agree with, but I'm just going to kind of try and state it in the best version I can, which is that when you encounter string theory, you encounter this extraordinarily rich and deep structure with many connections to quantum field theory, to gravity, many deep and surprising properties about it. And because the Planck scale is so large, i.e. gravity is so weakly coupled, the right intellectual approach is to try and study this, deep, mathematically complex, extremely intriguing, set of ideas, and to study it as deeply and as thoroughly as possible, and to try and get as full as understanding of it, with the idea that when you do get as full of understanding, by developing this full understanding, you will then be in the best position to understand then how this theory can be connected to the real world. Okay, so that is, I think, is a view a lot of people have, and it's a view I broadly disagree with. So what I would say is, so my view is that mathematical physics, this type of thing, has been on a sort of diminishing returns for the last kind of 40 or so. I mean, ADF-CFT is a big kind of peak, against the broad trend of diminishing returns. But there have been an awful lot of people working in this kind of way for a long time. And I think if you look at the kind of, say, the theoretical results, for example, the results about black holes of Hawking and Penrose in the 90s, these were both kind of extremely intellectually deep, extremely intellectually profound, with also profound observational consequences. So now I think you often have people arguing for kind of results that are deep, but they're really kind of quite divorced from observation. So my view in terms of applications to physics as a whole, mathematical physics has been delivering, which includes a lot of this kind of what kind of string theorists do, has been delivering diminishing returns for a few decades. I also think there's a danger, which is as follows: that when you have people who are working in theories in two-dimensional, theories in highly supersymmetric, but theories where there is no real attempt to make connections to the physics of this universe, and then they train students who are working in these areas, and then those students themselves become, is that you lose the connection with what it is to measure something. And so some of the research I've most enjoyed myself, is when you actually have to think about, you're trying to measure something. So you have a telescope or something. You actually have to understand how it works, how it actually gets data, what actual data is. You have to, when you actually think about how experiments actually work. And I think there is a structural danger in that you have kind of like at least two, sometimes it's possibly three kind of generations of people who get trained in an environment where they don't actually know, they've never really worked with data, and they've never really thought deeply about what it is to measure something in the real world. Now, the people of the older generation who were kind of, Peter's mentioned, like Ed Whitton, for example, are obviously, they grew up in the generation where the generation of the Standard Model, and they were kind of surrounded by this. This was kind of they were kind of just incubated in the thing of how you measure stuff, because that was just where they were. But as you go on to kind of as you move forward in time towards the present, then you have people whose entire career is where they haven't written a single paper which involves how you actually measure anything in the real world, and then their students haven't written a single paper in this. And it's like muscles. If you never use your muscles, if you spend your entire life sitting on a sofa, it's not the case that you'll then, by thinking deeply, you'll work out how to walk, and then you'll get up and be able to walk really well. If you never use the muscles, they're a trophy. And so my worry is that there is a danger that this is happening because people have never worked on how you connect anything with data, and then so they lose the ability to think about such problems.
Yeah. And I have a somewhat different point of view on all this, but because actually, people often characterize my views as my main criticism of string theory is that, it's not really, it doesn't have experimental backing, and so this is the main problem with it. But that's not actually what actually bothers me about it the most. I do have this great respect for experiment. I went through this. I spent some time working on a particle physics experiment early in my career, and that was actually a very extremely eye-opening experience in terms of understanding, actually why your theories are the way they are, and they're often kind of, our best theories are the way they are because they were kind of determined by what was measurable, what could be measured, and what couldn't. But the problem is that it has legitimately become very, very difficult to approach these questions about how to do better than the standard model experimentally. And we really are, we may already at this point with the LHC have basically run out of steam. And, there's a big argument about whether, to build another next generation accelerator. And the problem is that any way we know how to do it is going to be very, very expensive and not that big an increase in the resolution or the energy you can go to. So we are kind of stuck. I think the field, if you want to make progress on these questions, you may have to. I'm more sympathetic to. I think the point of view that Joe is less sympathetic to among his colleagues. That maybe you need to kind of go somewhere else for inspiration. Go to mathematics, or go to try and figure out how you can make progress on these things without having a connection to experiment. And I've spent most of my life in a math department, so I know. I have a lot of sympathy to kind of what the way mathematicians think and what mathematics works. But I think I see much the same phenomena that he's talking about from this different point of view. Even if you, like myself, if you're actually willing to say, okay, I'm willing to accept, maybe to put it in the most extreme fashion. If somebody tomorrow came to me with a completely beautiful, completely simple mathematical structure saying, okay, here's why the standard model works the way it was and why gravity works the way it was. But unfortunately, it's incredibly beautiful and simple, and they were right, and I agreed with that. And there was, but there's it shows there's no way for us to really get any more evidence for this experimentally. I would tend to say, okay, well, that I'm happy, that's great. Whereas I think Joe and many others would not be so happy with that. But even if you focus on the mathematics, I think he's right that there have been really diminishing returns. There were some just truly revolutionary, amazing things that came out of, especially the late 80s, early 90s, and this kind of overlap between math and physics, and a lot of it was generated by kind of joint efforts of Witten and Atiyah and Michael Atiyah, and they just completely they have wonderful for explaining some actual physical things, but they also are just completely revolutionary for mathematics. I mean, these ideas about the so-called Chern-Simons-Witten theory and the things that happen with three manifolds and four manifolds, they were just, and mirror symmetry, that they really have just revolutionized parts of mathematics. But watching what's happened since then, since the early 90s, it's just been kind of it's just been kind of a monotone decreasing amount of that kind of new insight coming in. At least, as I said, I often spend my day, get up in the morning and look and see what new papers are there in this field, and it's just saying the number of days when I see something, oh, that's actually something new and interesting, has just started to become vanishingly small, whereas it used to be a fairly common occurrence.
So here there's something I say in my book, and I've said this a few times, but it's the idea that you can buy from people in your language, but you have to sell to them in their language. And one of the reason kind of string theories grew so much and spread so much was this kind of part of this thing that Peter's alluding to, is that it was able to solve other people's problems and contribute to other people's fields. So this example of things like mirror symmetry in the 1980s, it was able to do things that mathematicians cared about. But it wasn't a case of you now need to start caring about quantum gravity and start thinking and care about our problems. It was able to say, these are the problems you care about, and we can solve these problems for you. And likewise with quantum field theory and holography, ideas like dualities and ADS-CFT. Again, there were a lot of people who were kind of quantum field theorists, and then there was this as well, you can do these calculations in gravity, and then using ADS-CFT, you can solve problems at strongly coupled quantum field theory, which people were interested in as quantum field theory. So this is one of the reasons I think string theory grew so much, particularly some of the people will say, well, there are all these models for quantum gravity, why is there so much on string theory? But I think part of the reason for this is that there were these times, a lot of things in the 1980s and the 1990s where string theory was able to solve other people's problems. And this is what led to the great. But I do kind of broadly agree with what Peter said. That I think ADS-CFT was a huge peak around 1997. But I think the test on this is so my friend Cliff Burgess calls this the kind of the ego test. Is kind of do you start advocating for ideas that aren't your own? And the sort of thing is, so the subjects that are kind of around theoretical physics, the question is, when do they want to start saying that, advocate saying, pulling in ideas from kind of string theory and saying, well, look, we really need these stuff to solve our problems. And I think this has happened a lot less now in the last, say, 10 years or 10, 15 years or something than it did in the 1980s and the 1990s.
Yeah. But maybe just to say one other thing about that. I mean, one thing, and this is actually one thing that I was trying to do that a lot in the book I wrote was to, the story of of these ideas that came in the 1980s, 1990s, a lot of them were, string theory was part of the story, but very much, only part. A lot of these really were ideas that were purely about, purely just very new insights into quantum field theory. And sometimes they had come about because people had been thinking about something in string theory and then realized there was actually something really interesting happening if you just looked at some related quantum field theory story. Anyway, there's an incredibly complicated and confusing story about a lot of these great mathematical physics developments of that era about their relationship to string theory, often which was kind of heavily oversold, or which is actually different than. Just for instance, I think people, I found it very, very hard to convince anyone of what something that is actually true, which is that Ed Witten did not win a Fields Medal for string theory. If you look at what he actually, it's just totally amazing thing that a physicist won the highest award in mathematics for some just amazing new developments in mathematics, and everybody assumes that this happened in the early 90s, and so during the period of string theory, and Witten was working on string theory, so this must be a Fields Medal for string theory, and it's just simply not true. If you look at the citation and you look at the actual work that he that had this deepest mathematical content at the time, it wasn't this actually wasn't string theory. But actually getting anyone, when I say this to people, I find it almost impossible to convince anyone of this. But anyway, maybe just to pick up one other thing that Joe had said, I think the other, so he was worried about, the way people being trained to do physics in a way that's divorced from experiment, has led to this kind of atrophy of certain kind of skills which are really important, and that's true. But I also think what I've seen, which I find very disturbing, is when I look at students now and I talk to them, they're, I remember being a student like that, and what you wanted to do was you wanted to say, how do I get to the cutting edge of the subject and to the really newest, most exciting ideas that are moving forward as fast as possible? This is what you want to do. And so what it causes them a lot of to do is to really skip over really learning quantum field theory. So they take a quantum field theory class and they do some problem sets, so they learn how to do a few computations, but then they immediately are then trying to do ADS-CFT or string theory or anyway, whatever the hottest topic is of the year. And I'm really increasingly worried that, the system has trained, a couple generations of people who don't actually really understand the standard model as what the quantum field theory issue, as a quantum field theory, what the actual technical issues behind it are. And, that they've ended up being trained in topics which aren't that fruitful, while completely skipping over, just the real fundamentals of what the problems are.
Let me come in on that, because that's something where I think I don't really agree with Peter. So if you take, for example, Peskin and Schroeder, so this is a well-known quantum field theory textbook. Loads and loads of people learn quantum field theory through Peskin and Schroeder. And you see what it's structured to. So Peskin and Schroeder kind of builds up to, one loop precision electroweak calculations in the standard model. And these were kind of, at the time it was written, kind of the LEP collider was doing lots of precision electroweak tests. And I think it's true, very, very few students learn, are kind of fully on top of precision electroweak. But then I also think that's, the subject changes in that the calculations that you need to get, you need to be really in the weeds of, they do change with times. For example, you could argue now that, knowing gravitational wave emission and understanding gravitational waves or understanding the physics of axions is more important for people who want to be connected to experiment than understanding, how to do by hand, one loop calculations in the electroweak sector of the standard model. Because it's also true that the people who do kind of standard model calculations, they're not doing them by hand. They've all got codes to do them. Mm-hmm. So I do think it's true that the skill set changes with time, and the kind of the problems you can be where you can be fully conversant with all the kind of nitty details of it just change by generation, and it's kind of right that it changes by generation. So I don't know whether that's exactly what Peter's referring to, but that
sorry, just before, I also don't see it as something that's your critiques, Peter, as being about this generation. So as I was preparing for this talk, I went through the critiques of string theory that you have, Joseph, which are, you're not a fan of the overhype in the same way that you're not a fan of the uninformed criticisms. Both do damage. You see that there's difficulty in constructing de Sitter vacua because you require a delicate balance of multiple contributions to the potential. There's also the scale separation in ADS-CFT, and yes, ADS-CFT is powerful, but constructing compactifications that correspond to scale-separated CFTs, where there's a large hierarchy in operator dimensions, is difficult. And I know that's relevant for realistic moduli stabilization scenarios. I'll put some of your work on screen. There's also the G2 compactifications in M-theory, which, unlike the Calabi-Yau manifolds, which are complex, these ones are real, and there's a palpable lack of examples of compact ones with the singularities necessary for the non-abelian gauge theories. Now, Peter, your critiques of string theory are that, unless I'm mistaken, they don't have something to do with this new generation being trained without being tied to experiments or without knowing the fundamentals. When last we spoke, Peter, you spoke about the lack of predictive power and this huge landscape, which is even larger in F theory than it is in regular string theory, that there's no consistent non-perturbative formulation. Also, you both agree on the hype, and you think ADS-CFT is a distraction.
I'm not gonna. I'm not concurring with. I mean, I think ADS-CFT is a profound and important, discovery which gives us real, deep, true conceptual insights about nature. I'm not signing up to it being a distraction.
Well, I would love to have you all speak about that. And then the other 2 or 3 that I recall are that the claim that it's mathematically rich is true, but that doesn't validate it as physics, and that there's an ignoring of alternative approaches, epitomized by it's the only game in town. So does that correctly summarize your respective critiques of string theory?
But Kurt, are you trying to characterize my views, or are you bringing?
Yes.
I think not Joe's. I think Joe is not going to be on board with all of this. Yeah.
No. Just the first few were Joe's up until Joyce Manifold. Then the rest were yours. Anyhow, the point is that all of what I've stated, I don't see as being unique to this generation. I see it as a critique you could have said 20 years ago.
I remember when I came into the field. So I was an undergraduate. I was really fascinated by this. This was the mid 70s, and so to me, from the beginning, what was the cutting edge was the standard model. So everything was my whole kind of conceptual framework of how do I think about what I'm trying to do here is I want to learn as much about the standard model as possible. I happen to be also very interested in mathematics. I want to learn as much about the mathematical structure of the standard model as possible. I want to learn about the non-perturbative issues in the standard model. And so this was how I was brought up, and this is what my whole motivation was about. I see the last few generations now going back 20 or 30 years of students, coming in with a very different thing. The things which to me seem kind of really the most central deep issues, which there's still something there we don't understand, which you need to work on. That's just something they've kind of skipped over. I mean, Joe is pointing out to one thing about a typical standard. Maybe just to say one slightly technical thing, quantum field theory textbooks. If you look at them, they're mostly fairly similar. I mean, they do things in different ways, and they have different virtues and different problems. But they really are aimed at showing how to do these kind of perturbative calculations in the standard model, like as he was referring to. And there's a certain technology for doing that, and they're training you how to use that standard technology. I mean, what they're not, the problem is what they're not doing is they're not really kind of telling you about any of the technical problems, about what things are still, and to me, the kind of central question, what is still unsatisfactory about the standard model? What doesn't really work right? And that you don't get out, it's very hard to get out of a quantum field theory textbook. Anyway, it starts to get to be a little bit more complicated, but I really see a big difference between kind of the environment in which I was trained and what I was focused on, and I see that what students these days, how they're being trained and what they're focused on. And I think the thing that to me I think was most central, and I think still is a most central question in our subject. I think they're really kind of they're trained pretty much to ignore, and even worse than that. This is a field with a lot of intellectual arrogance, and it's a very, very difficult subject. People kind of come into this environment thinking, well, I must, anybody who understands this stuff like me is a real genius. I kind of understand it. I must be a genius too. And the other people also come out of the standard educational experience these days, not just being unaware of things they should be aware of, but at least somewhat morally convinced that, anybody who cares about those issues is somebody who just never understood the textbook. These are old textbook issues which have long been settled. And, if somebody is kind of trying to bring these things up and talk about them, it must be, they were just one of these students who kind of, never really understood the textbook. And that's a little bit exaggerating, but it's
So there's one thing where I want to speak in defense of students. So I think this also something applies with experimental particle physics. So I think with students, I think students really need a chance to People need to, when young people want to do something, they need to have a chance to have a career. And I think this involves a certain thing where the thing where you're going to work hard on something, you're going to work really hard on something. It may not work out, but then you get your lottery ticket or your ticket, you get your chance of you work really hard, and then there might be something kind of really big. So experimentalists get this. You had this with the LHC, for example. Yeah, they work really hard. There's a chance of discovery, and I think it's really important that people have they have the chance of contribution. And so I think while I have some sympathy with what Peter is saying, I think it's also from a student's point of view. I mean, it's really hard to be the idea that you're going to say, well, we've got this standard model, and Weinberg at his peak was spending huge amounts of time thinking about the structure of the standard model. Witten has been growing up thinking about the structure of the standard model. And so this is an area where there's been a lot of extraordinarily smart people have been over and been over and been over. And so this is why I think you can fully understand why students would want to go something where they're going to something which is maybe less explored, and then they feel they have a kind of crack. So I also want to pick up on this comment on arrogance, which I think is kind of interesting, and I think it's true, but there's also a sense in which I think it's important, it's true, and I think it's kind of I want to kind of explicate this a bit. So this comes back, if you're a student and then you think, well, okay, you're a student in particularly, and you want to make, and this is kind of held at every time in the subject, and you want to make a contribution to the subject. And if you think too hard about the idea of, I want to make a contribution, and Weinberg's been spending his career in this area, Witten's been spending his career in this area, Wilczek's been spending in this career, or the previous generation, you say, well, Heisenberg's been thinking all about this, Dirac's been thinking all about this, Feynman's been done, and if you kind of worry too much about this, I think you will just collapse under the weight of what you're trying to do. So I think the healthiest attitude for students is, almost some simultaneous combination of kind of almost extreme arrogance and extreme humility. Not just one or the other, but somehow be able to hold them both at the same time. Because on the one hand, you really want people to be saying, actually, I think all these people who are genuinely obviously super smart, have been in this area before me, have been thinking about this before me, but I can make a contribution and do something none of them do. I can do something that Witten didn't do, that Weinberg didn't do, that Wilczek didn't do. And to be honest, some degree of arrogance is going to help. Helps in that. Otherwise, you just collapse under the weight. But then you also need the humility of saying, all these extraordinary people have been here before me. I need to learn from what they've done. I need to learn from the best of what they. And so this is, to my view, I mean, theoretical physics has a justly deserved reputation for arrogance, but I think there's also a big element of humility too. But I also, and this is the kind of thing which is maybe slightly controversial, is I think this arrogance is actually a structurally positive part of the subject, because the subject could not make progress without it. Because otherwise, if you think about what you're trying to do, people will just wilt under the expectation that the idea that you could be 22 or 23 and you've had thousands of really smart people in this area before you, and you can do something that they haven't done. But it's needed, we constantly need 22 or 23-year-olds thinking this in order for the subject to make progress. So this is my slightly nuanced view on arrogance in theoretical physics, and why it's actually a structural and ultimately a structurally positive part of the subject.
Why would you say arrogance and humility versus confidence and humility? Why do you say arrogance over confidence?
So I mean, this is coming back to the thing that the rational of evaluation of anyone is if you are saying, look, Feynman's been thinking about this, Weinberg's been thinking about this, Witten's been thinking about this. Can I do this? I mean, I think, if you are going to rationally say, well, I can rationally evaluate myself as, I'm not talking about me here, but someone could rationally say, well, I'm confident I could do better than Weinberg or Witten or Feynman. I don't think that's, it's not, you can't do it rationally. It needs, I think actually this sort of slight, somehow arrogance, but the ability to recognize its arrogance and that it needs to be completely balanced by humility. This is why I said it's something you almost, I think the ideal thing is to have both of these on your shoulder at the same time.
Yeah, I should make clear, I pretty much agree with Joe. I should make clear that this kind of this wasn't completely a critique about arrogance. I mean, I'm just been sitting here telling you about how Ed Witten is wrong about something. I mean, I clearly have plenty of arrogance to go around myself. He's right. You need some real, some intellectual self-confidence and ambition, to get anywhere in these kinds of very difficult subjects. But at the other time, you also need the humility to realize that you're quite possibly wrong about things, and I think math. It's a very interesting experience being in a mathematics department, because mathematicians are the whole thing is about these very precise issues of exactly what is right and exactly what is wrong. So mathematicians are actually quite used to the fact that most of the time, or very often, you're going to be wrong about something, and it's going to be completely undeniable because it's going to be an issue of rigorous mathematical proof. So anyway, I agree that this intellectual ambition and arrogance of a sort is, especially of the young, is a good thing, and is what kind of leads to progress. But this was just kind of a more of an issue of the way this shows up is. It does become a problem in this particular context. When the field itself is not that healthy, that there isn't it isn't making a lot of progress, and ideas that are being promoted as the latest ideas are not working well. Then, the danger of being an arrogant student coming in is that you might actually believe this, and this will. Anyway, you'll lack the necessary understanding of what's actually right and what's wrong. But I think Joe started to talk about something which I think maybe we should talk about, which is related, which is this question of of careers. If you're a young person, your other main concern, besides whether you're arrogant and smart than other people or not, is are you going to be able to have a career? Are you going to find a job? How are you going to whatever your intellectual goals are, what you want to pursue, is there going to be a way for you to do this? Are you going to be able to support yourself? Are you going to be able to have a real research career? And how are you going to go about this? And I think that's really a real fundamental issue, and about why. And if you do agree that there's been some problem that with the field not making progress that way it should be in recent decades, you have to kind of ask yourself, what is this part of the problem? What can be done about this? What can be done to actually change the reward structure so that ambitious young people actually can work on more promising things and still feel that, as Joe says, they have a shot, they have a chance to actually do something.
Here's something I'd like to say, which I think this is not something which is at all unique to string theory or particle. So I saw recently a quite an interesting plot. So this was from the US. This is I think the National Institute of Health. They have something called like R1 grants. And these are the grants which basically go to kind of start when people start a lab of their own. And what the plot was, it was the percentage of these grants that go to people under 35 compared to the percentage of such grants that go to people over 66. And so this has kind of gone from 1970, it's something like, maybe like 35, I don't remember the exact numbers, but roughly something, so like 35% are going to people under 35, 1% of these are going to over 66. And then you come to today, and the numbers are sort of inverted. That there's a very large fraction of these grants are going to people over what would used to be a retirement age, and a very small fraction are going to people under 35. And I think you can see similar things in kind of fundamentals, particularly with things like the Simons Foundation, and this habit of some private foundations giving extraordinarily large sums of money to very senior people, basically to run their large numbers of junior researchers in their research program. Whereas I think a much more and you have similar things like these Simons collaboration again, which are kind of very very large, very well funded things, but are basically are kind of very much supporting established research. And I think the ability to give young people their head, give them enough money that they could properly do something by themselves without relying or feeling that they have to sort of sit in the network of someone much more senior. And obviously not all these things will kind of work out. And so I think this is a sort of structural weakness in terms of for the subject. But I don't think it's particularly unique to string theory. I think actually across a lot of the sciences, I think this has been a change over the last few decades, that it's much harder to get started. Yeah, the idea of getting to get started young and to get independence young.
Great. Now, as I mentioned in the introduction, I would like this conversation not just to focus on string theory, but also theoretical physics. What are the problems? So you just mentioned that there are disproportionate rewards that go to senior individuals instead of the fresh talent. What else? And I understand that this doesn't just affect whatever we're about, or you all are about to speak about, won't it just affect theoretical physics, but perhaps science as a whole. But let's just speak about our domain of theoretical physics here. So what are the problems actually with fundamental theoretical physics, as theoretical physics as a whole is quite large?
I mean, I think the obvious one is that of experimental data. I mean, I think maybe people's views on the subject, I mean, Peter's from a generation where the standard model was being discovered in real time, as it were. If you look at, there's a period in the 1970s, the late 70s, where particles are kind of discovered, not quite at the rate of one a year, but almost at a rate of one a year. And I think what you experience when you're young inevitably sets your notion of what kind of is normal or what should be normal. I mean, my PhD's in 2006. Higgs discovery. I'm from very much the generation where almost your expectation is every single time you try and break the standard model wins. That's been the pretty much throughout my career. Obviously, there is physics beyond the standard model. We know there has to be physics beyond the standard model. But in terms of your expectations, your default thing of what happens, I mean, we were formed in very different times.
Actually, not that different than you think. I mean, there's also the I started learning about the standard model in 75, 76. It was already in place, and this phenomenon of that as experimental results came in, they all, anyway, there was a lot of excitement that everything was agreeing with the standard model. But I think it didn't take that many years to start to become a little bit depressing. That, wait a minute, it's great that we're so successful and everything agrees with the standard model, but if we don't have something soon that disagrees with the standard model, we're going to be in trouble. And that this goes way back. We've been in that situation for a long time.
Also, I mean, hype is not a new thing. I mean, as you may be aware, supersymmetry was first discovered in 1984 at CERN at UA1 and UA2. Yeah, I think it was undiscovered in 1985 or but it was I mean, so claims of kind of discoveries, hype, which are things which are not subsequently justified. I think they've always been there.
Maybe to try to address a little bit, I think what you're trying to get at. I mean, one is there's technical questions about what we might see as how to make progress, and I'm in this very weird state of the last few years. I've actually, some old ideas which I'd long convinced myself couldn't possibly work, all of a sudden I started to see ways forward with it, and I've been very happily exploring those, and I actually think this is really going somewhere. So I feel myself in this question of what's the future of the subject, what's the right thing to be thinking about. I feel like I start to become like every crank in the subject. Yes, well, I know what the right thing is, and I'll tell you all about how twistors and this and how this is the thing to do. So, there are various ways of thinking about twistors. Hitchin's way of thinking about them and the relation to hyperkähler manifolds, I've actually kind of realized that that's actually a better way of understanding the relation to some of the other things that I've been trying to do. So, and there's this, maybe just to say a couple words about the whole thing, it's really just, there's a fundamental idea in twistor theory is that a point in space-time should be thought of as a different kind of geometrical object, as a sphere. If you like, maybe when you open your eyes and you see the celestial sphere, that sphere is the way you should describe a point in space-time. Or mathematically, it's also equivalent to saying that if you're looking at the vial, like let's say the right-handed vial spinners at a point, that you should actually describe the points in space-time by using those spinor spaces. So in some tautological sense, if you want to know what a spinor is, in this geometrical setup, a spinor, the space of spinors at a point is the point. And so there's a long story about this, but it I'm seeing quite a lot of different ways of seeing the symmetries that really govern how the standard model works, fitting. There's a new way of thinking about them coming about from this geometry, and that I find very promising. And maybe that's the best to say, but it really is kind of work in progress. But I keep finding them. That unlike most ideas I found in my life, that I've had in my life, I found that if you think about them for a while, sooner or later things just kind of work less and less well, and you realize this wasn't such a great idea. This is actually something that just kind of keeps doing something interesting, and that I'm quite excited about. But I can understand. I mean, anyway. There's a lot to be done to get anyone else interested in this.
If falsifiability is not immediately achievable, then what are the other criteria that one should use to evaluate between different competing theories of fundamental physics?
I think so. Something which is, there is an intellectual depth and an intellectual richness of string theory, which I think it's the more people kind of are able to evaluate it at a technical level, the more people agree with this. And now you can say it is an aesthetic judgment to say that ideas which include quantum field theory, include general relativity, and are very kind of rich and complex and kind of hold together in lots of non-trivial ways. So it's an aesthetic judgment to say that probably nature doesn't leave this out. Yeah, you could say, well, you could have this structure, and if you were going to say to me, yes, string theory may be mathematically beautiful, it may be intellectually rich, there is no logical reason why that means it has anything to do with nature. I can only agree with you. There's no logical reason. That is not logically implied. So there's an aesthetic judgment that things which are really mathematically subtle, mathematically complex, and somehow tied to a lot of what we already know to be true, are not left out by nature. So that's what I would say, and that's part of that's an aesthetic judgment.
And I in some sense agree, though. I think my own aesthetics and the mathematics and the things that I've been interested in, I think I see this differently than Joe. String theory, it's true, it's a very rich subject, but I've always thought that to some extent it's a very rich subject, but in some ways, because it hasn't really worked out. If this had worked out in 1985, and you'd found that there's some certain Calabi-Yau that gave you the standard model and this all worked, it would be a fairly complicated and very interesting theory, and it would be and that amazingly works described as the real world. But instead, that people had trouble getting that to work out, so they started on a very, very long intellectual journey by some very, very smart people, and they ended up exploring all sorts of very, very different things and discovering all sorts of interesting different things about mathematics and about physics. The problem for me has always been that, to the extent that I find the things that they're discovering really compelling and really, really beautiful, they often were orthogonal to the things that were looking like the real world. That when you tried to move this in the subject and try to get something that looks like the real world, you had to move in kind of not so aesthetically pleasing directions. Whereas if you'd said, I'm going to follow, my aesthetic judgment that what is a really deep idea, what's something worth looking at, totally independent of whether it agrees with the experiment, you ended up going in directions which don't so much look like the standard model or look like the real world.
Can you give an example of where you've had to move away from what's aesthetically pleasing?
Well, anything, even mirror symmetry again is an example. It's there's beautiful mathematics there. It just doesn't connect very well to anything about telling you about four dimensions. maybe ADS-CFT is also somewhat of an example that you want to, it works really nicely in 5 dimensions, in 5-dimensional space-time. If you try and use it to kind of say something about real physics, about 4-dimensional space-time, or you use it to try to solve QCD, you end up just kind of struggling and having to try to go to something more complicated. The really beautiful thing that you were saying in 5 dimensions just is you have to kind of move away from to try to get to a physical dimension or a physical situation.
The question that I just asked was about what is it that should allow us to decide between competing theories when we don't have experiment to guide us. So in other words, when we don't have something objective to guide us, and then Joe and you, Peter, you both said, well, aesthetics, which a synonym is beauty or elegance, but yet you both find different aspects of the world beautiful and elegant, and so that doesn't converge.
Yeah.
So one thing where I can I come say where I think we might where I kind of both agree and disagree with Peter is that so Peter says that the bits that when you get to the real world that you lose a lot of this beauty. But so what I would say is that when I talk about the beauty and the aesthetics, it's talking about this is a judgment in terms of the theory, not necessarily in terms of the solutions. So that, for example, if we were going to talk about, simple gravitational things, you'd say, well, okay, a sphere. A sphere is a very nice, aesthetically beautiful and simple object. But if you want to talk about the Earth, for example, then it's very important for the history of humanity that there are continents, that there are some continents are more separated than others, and then you have to get into very much the specific weeds of these are the precise details of the actual realization, and no actual planet is just a perfectly sphere. So in this way, my aesthetic judgment is relating to the theory. And, I agree with Peter that when you try it saying, well, now you want something to look as close to the standard model as possible, it's no longer the kind of, maximal beauty and simplicity of, for example, maximal, you've got some kind of messy compactification. So there'd be some kind of, the fact that the standard model might be kind of some particular contingent detail of that. So in that sense, I agree with Peter, but then I disagree because my aesthetic judgment relates more to the theory as a whole.
Yeah. I understand. I mean, but the issue is more about, it isn't, the issue is more about the kind of structure of the theory and the problem than about the actual solutions. You may have complicated solutions to that's true. But maybe I want to say one other thing about this. This is something I did try and write about in my book, and there was kind of about exactly this question, how do you evaluate things when you don't have experiment to keep you honest? And there's kind of a line from a Bob Dylan song that kept going through my head. It goes something like, to live outside the law, you must be honest. And I think what this means to me is that if you're going to do this, if you're going to, not have experiment telling you whether you're right or wrong, and going to rely upon, aesthetic judgments or your own judgments of what's really consistent, of what's really a compelling idea, you really have to. You really have to be very honest with yourself. It's very easy to fool yourself. It's extremely easy to fool yourself that some idea is beautiful and wonderful, and even when as you learn more about it, you find out this is really not such a great idea. So you have to, and this is actually kind of what I see as one of the kind of fundamental problems of how string theory has been pursued, and especially the problem of hype. That I think, I think the whole field of fundamental physics, and especially string theory, has just suffered a lot over the decades from, this kind of, to put it kind of bluntly, a lack of honesty about, what has really been going on here. And it's very tempting. It's very easy for people to go out into the world and write books and have TV programs and promote, so that everything here is so great. But, it's doing that is very, very dangerous if there's no experiment to keep you honest. And you really need, Anyway, so the whole subject really kind of needs some kind of much better internal structure of kind of acknowledging when things aren't working, and keeping track of what really works, what really doesn't work, and kind of not running out and issuing press releases from your university about how great something is, about what's going on when it's just not. And so that's been a large part of my kind of feelings about the subject over the years.
So here I'm going to come in and, I'm afraid if you want to fight here on this point, I'm going to largely agree with Peter that I think, like, and what I said earlier about, intellectual ambition, arrogance, strong personalities. Now, I think even though this may not lead to the people who are necessarily quote unquote nice, but I do think that is always kind of a part of, a necessary part of making progress in fundamental physics. But ideally you have experiment that kind of, can kind of tame this, as Peter says, that the thing that experiment is telling you are wrong, and this has something to do with, and this has an ability to tame, strong personalities, people who are strong personalities, intellectually very self-confident, and experiment does have an important role in taming that and keeping everyone on the straight and narrow. And I think there is a kind of a structural danger. So in terms of how you make, so I said earlier on, in terms of the kind of, are things optimized to make progress? And I gave that a C. And I think there is there is a definite danger when you lack experiment as the tamer, and then you have the danger of hype where people, you have prominent newspapers, people send press releases to prominent newspapers write big articles about writing things up as massive progress, which in reality are not massive progress in nature, and in the long term the subject suffers, because if people get the sense that you are not communicating honestly to the public about what you have done and what you haven't done, then in the long term you suffer. And this is why I said, when I come back to this thing, you said, well, there's no direct experimental evidence. I think it's important to say that, because it's true, and we've got a responsibility to the public to communicate honestly. And I also, when I say that I think string theory is an extraordinarily deep and rich intellectually structure, and I think it is probably part of nature. And I also say I'm putting that equally up there with that there is no direct experimental evidence, because I think both of these are true statements. But when you go to the public with press releases or articles in newspapers or these kind of very kind of puff write-ups by certain kind of online science magazines, then that does damage broader confidence in the subject and broader confidence in the academy.
Yeah, Scott Aaronson was just interviewed alongside another professor of quantum computing, I believe was a professor or researcher in quantum computing. And then that researcher was saying, look, I don't feel the need to counter the hype in this field. All I care about is that if I'm correct or incorrect. When I publish something, is it correct? That's what I care about. And then Scott quipped, he said, well, the fact that you don't feel the burden just doubles the burden of other people.
Yeah.
Okay, so I want to get to what you disagree on. There's too much agreement here.
Sorry. I was afraid that would happen.
So what is it? Joe, when you've been listening to Peter, what has stuck out with you as like, okay, that's the point that I want to pick a fight?
So one of the obvious things is all my career is working on connecting string theory to particle physics. That I think string theory is an abundant source of rich ideas for how you go beyond the standard model of particle physics. And if you read Peter's blog, he will generally say that this sort of stuff is all a waste of time. Or I think this is what he says: is all a waste of time.
More or less.
and is not what you were doing. So this is an area. I think string theory is an abundant source of rich ideas for think about how you think go beyond the standard model. And I think Peter thinks this is all probably at best a waste of time. Yeah.
So then, wait, to put you on the spot some more, Joe. The common critique that you'll hear on places like Twitter is that those who critique string theory, they just don't know the subject. They're uninformed. They're not bright. Peter's clearly none of these adjectives.
Well, bright people who are informed can also be wrong. Yeah, that's not in itself. That's not in itself a particularly strong point to say that someone is bright and well informed. To say that, therefore.
Well, I mean, anyway, I think my disagreement with Joe, actually, it's been my long-standing disagreement, kind of since the beginning and over the long term, especially like with my colleague Brian Greene, for instance. It was always that not that I just always thought, okay, he's got some enthusiasm for a certain picture of a world, for a certain set of ideas, and I look at them, and from fairly early on, I wasn't very. I lacked this enthusiasm, and as years go on, it just kind of looks. I feel more and more justified for this lack of enthusiasm, but so the big difference you're seeing between us is really just we're looking at different kinds of trying to see a way forward through to a better theory, a better understanding. There's certain set of ideas involving string theory, which some people significantly smarter and harder working than me I find very 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 compelling, and it's part of it is also that I've always, because of my own particular interests and the way I've learned the subject, there were always different things which seemed to me kind of most intriguing and most promising. And for many years when I would write about this, I kind of felt that, well, I've only got kind of the vaguest, if people ask me and put me in the spot, is I've only got kind of the vaguest ideas about, maybe you should be doing this kind of thing, not what you're doing. And now I feel I have something much more specific to point to. But it's, anyway, we come from different backgrounds. We know different things. We see this whole problem and this whole structure everything in a different way. So people quite legitimately are making their own decisions about what they think is the most promising thing to do and to think about. And anyway,
can I come here, because I think I maybe can express something. So I'm going to try and express a criticism which I think I've heard Peter make, and I've certainly seen other people make, and then I want to explain why I think that criticism is wrong. So the criticism would go something like this. If you're trying to connect string theory to particle physics, then you need to compactify the extra dimensions onto something like Calabi-Yau. There are something like 500 million known Calabi-Yaus. The number of ways when you do this, you just sort of ensure that what are called the moduli are stabilized, that the kind of geometry is something stable. You often need what are kind of fluxes, and if you don't know the details, it doesn't so much matter. But let's say which common ground, which I think we'll agree on, that there are an astronomically large number of ways. The number 10 to the 500 is often quoted here for turning these fluxes on. So the argument that is then given is you want to connect string theory to particle physics by compactifying on a Calabi-Yau. There are something like 500 million, however many Calabi-Yaus. There are something like 10 to the 500 ways of turning fluxes on. There are something like 10 to the 500 possibilities for what you are doing. Every single one of them will give you different low energy physics. You've no possible chance of finding the correct theory. You would never know if you do. This is worse than the needle. Every compactification will give you different physics. Therefore, you're not going anywhere. There is no kind of intellectual value or worth in what you're doing.
So just to say, Joe has done an excellent job of channeling me or people with this criticism. Go ahead.
Mm-hmm. And actually, that's going to be the preamble to the next Ed Witten, what everyone should know about string theory.
Right. So then what I would say in response is that it's not there are various aspects of the physics of these compactifications that are actually universal, that across these 10 to the 500, these all these fluxes, that there are certain things that are kind of always present. So that, for example, one of the things that I've worked on a lot is the presence of what are called relatively light moduli. So these are particles whose essentially all interactions are gravitational strength. And these can have profound impacts on early universe cosmology. They can come to dominate the entry into the universe in lots of you very often get the idea that the universe could be filled at an earlier stage. So the universe is unconstrained roughly for about 30 orders of magnitude in time, about half its lifetime on a logarithmic scale between inflation and nucleosynthesis. And this period of the universe, for example, could be entirely 100% dominated by string theory particles, by moduli. And the presence of such moduli is completely ubiquitous across these 10 to the 500 compactifications. So what I would say in this kind of thing is that it's not actually true that the particle physics is all different. There are lots of aspects of the physics that are actually broadly universal across these things. These lead to very interesting modifications from, for example, the standard cosmology. Such modifications are reasonably well motivated, and they could well have been part of the history of this universe, and therefore it is right and proper to do as I do and other people do, to say what signatures could these give rise to, how in principle could you look for these, how in principle could you detect these, how in principle could you say that the early universe, in this period where it is currently observationally unconstrained, this is open, we don't know half the history of the universe on a log scale. How do you look for the physics of what happened in that time? And the string theory suggests lots of interesting things that could happen there, and these are very worthwhile things to think about. So that is why I think the criticism is, and why I think the criticism is wrong.
Yeah, though, but then your fundamental problem with that is that no one is. I mean, you're correct that these issues about moduli and seeing effects of moduli is a generic issue in these kinds of theories, but you're seeing it as an opportunity, and it's a legitimate thing to do, to go out and ask, can we actually see these things? But you're still stuck with the fact that we haven't seen them, right? So you don't. You'd be in a much better shape if there were a couple of fields out there which looked like moduli fields, and then you'd be in much better shape.
Yeah. I mean, here this is coming back to the thing that I think the particle physics really as a whole has missed over the last few decades is really striking new data. Yeah. And data is the foundation of the subject. And in this I include then there's lots of parts of astroparticle physics, for example, the search for dark matter, for example as well. Yeah.
Okay, so then given this lack of data, Peter, you mentioned that one of the problems of the way that fundamental physics research is conducted is this lack of honesty. Are there other issues?
Well, I don't know. I mean, there's a lot of different. Anyway, it's a very complex. It's a complicated subject. There are a lot of interest. There are a lot of different things to say. I mean, one of the issues. Well, we've already dealt with a lot of these. I mean, one is I think the kind of career issues about how you and I understand. I think Joe's right that there are related problems in other fields, but there are some this is exceptionally bad and exceptionally a problem in fundamental physics in general. That if you are an ambitious young person, you want to do something new in the subject. How. First of all, it's very, very difficult to come up with a good idea for somebody to do. But the other question is, it's also very, very difficult to find a way to support yourself in a job and to fit into the funding structure as currently. And
can I just cover here? So one thing I'm sure Peter will agree. So one criticism you sometimes hear of string theory is that string theory is robbing all the money that should be going elsewhere. So I think it's worth making completely clear that the amount of money that goes to particle theory as a whole is a tiny fraction of what goes to experimental particle physics, which is a tiny fraction of what goes to condensed matter physics, which is a tiny fraction of what goes to kind of medical physics. Yeah, the idea that if you consider the science funding pot, that somehow there's a huge chunk that is going to string theory or any kind of fundamental particle physics is completely whatever. Peter's never made this criticism, but you will find this criticism made quite a lot on Twitter.
Yeah, I think that's a good point to make. Right, I can agree. I mean, that's really not the actual problem. I think maybe a good way to focus on the actual problem, I think, is to be an experience, which I think Joe has probably had. I've had in that more on the math side is when you're an academic department, part of what you do is hire people and try to reproduce yourself. And so you're sitting there looking at these folders of people's applications, and you have to decide, who are we going to hire? And it's I think it's kind of the problem is that the people do put in that position in theoretical physics, at least to my mind, there's part of the problem is that they have a lot of applications. So they have many talented people with very, very good credentials coming from, very well-known places. And so they're not, if there were a lot of jobs out there and it was hard to hire people, you could, if somebody came to you and said, well, I'm not working on the latest, the ideas have got all attention. I'm doing something a little bit weird on my own, and I have this other thing I'm trying to do. You might hire them just because they were better than they seemed a bit smarter than the other people. The problem right now is if you're looking at this stack of folders of very smart people with these very, very good letters saying how brilliant they are and who are quite talented, what happens, at least I'd be interested to hear what Joe says about this, but in my experience is that, people then say, okay, well, now that we have this stack of these very good people, we can kind of focus on people who are, who are, can come here and can be part of what's currently the kind of leading edge or the latest, hottest new idea. And so you end up with a hiring system where people have to be, they have to be really both smart and talented and do everything right, and they have to kind of seem to be saying something about the newest, hottest idea in order to get a job. I don't know what your reaction to that is, Jim.
One thing I think there's a difference between sort of US and European hiring. So for good or ill, and yeah, it can work different times. I think I think that is more true of US hiring, I think, than European hiring. I think European hiring is more willing to, tends to be less kind of fashion. I say fashion driven sounds slightly as it's necessarily a bad thing, but the kind of positive side of this is sometimes problems that need a lot of progress is to be made, and by just throwing a lot of people at this problem and hiring everything at the problem, you make an awful lot of progress quickly. So I don't know, it's not necessarily true, but for good or ill, I think what you're describing, where people have to be working on the latest hot idea, is more true of US hiring broadly than your European hiring.
Okay.
Yeah. I think also one thing just I want to say is about when Peter was talking about Witten, the Fields Medal, and it's not the strict, is that the idea that good scientific fields, aren't surrounded by kind of high walls. They're surrounded by kind of very low, boundaries you can step easily over. And so the idea that kind of people are, string theorist or not string theorist is really kind of not true. I mean, people can work on many, like for myself, on one level, I'm a string theorist. I've also done work on kind of searches for axions with X-ray astronomy. I've got these various, these sort of different legs in kind of like things like cosmology and astroparticle physics. On the more formal side, you have people, you could call them string theorists, but you could also say they're kind of quantum field theorists. There's been lots of kind of reasonably active areas in quantum field, for example, the Bootstrap, for example, which has relatively not huge connections with string theory. And the idea that people aren't on string theory or off string theory. It's not necessarily you're in and out. I mean, good fields are healthy. People can kind of wander across between what's tightly, you could call string theory and what's not string theory. I mean, I think the more broad thing is, are you having things which are to maximize the conditions for intellectual creativity and intellectual productivity, and for kind of and for interesting and important ideas to appear. Which also I think this other thing is saying is that you often can't tell on a 1 year timescale or a 2 year timescale what are the most interesting and important ideas.
Yes, I mean, what I was talking about, I've seen this happen. I mean, to some extent, this also happens in mathematics. It's much the same thing, but there, when you have a very healthy subject, where the things which are kind of the hot topics or the fashion or whatever are actually really legitimately kind of exciting and major sources of progress. It's it's a perfectly reasonable thing to be doing, and academia moves along quite well. When if you've kind of gotten into trouble and if the fashion-driven things are not really working, then it becomes more of a problem. But maybe to get to something else that related to what Joe was saying, I think one of the more disturbing things I've seen happen in this subject over the years has been this kind of, this business of, who's a string theorist and who isn't a string theorist. There's this weird way in which it's become kind of tribal, and that, people feel that, either you're a string theorist, either you're part of the tribe or not of the tribe. And if you're a string theorist, then you have to, you have to defend. You have to defend string theory against these, outsiders who are going to kind of coming in and trying to just to steal your funding and your jobs, and there's a really and I kind of noticed this most when I was kind of starting to write about string theory and to criticism. It was really kind of shocking the extent to which you'd talk to people and they would say, "Yeah, I more or less agree with you, or agree with you a lot, but I wouldn't dare to say any such things publicly because that's going to get me in trouble. I'm going to have trouble with my next grant or my students having jobs, or this has become kind of a toxic situation where you don't want to you don't want to be caught saying the wrong thing, and that people in my tribe are all of a sudden going to want to get rid of me." And then I realized after I'd started the blog, at first I was thinking, well, anonymity is important on the blog comments because it means that people who want to be critical of string theory are going to be able to do so without retribution. And then after a while, I realized that the way things were going, string theorists also needed anonymity, because if you were a string theorist and you decided to kind of come and comment on my blog and forcefully defend the theory, then you may offend people from the other tribe and you may get in trouble, and you don't want to do that either. So it's been anyway. It's something actually, quite bad intellectually to make it to have it be so difficult to actually, have these kinds of discussions.
Yeah, so I do recognize some of the dynamic you're talking about. The idea that it is, coming back, the idea that you have some number of certain people are very powerful at certain elite universities in the US, and people don't want to criticize them, or they don't want to criticize their papers, or they don't want to say that it does. This paper's wrong, and because people either fear, and rightly, that their career would be impacted by that. So I think that is true. I mean, I've experienced this a little bit myself. Sometimes when I've kind of early on in some of the papers I've written, and so I think it's a true, and I think it is, and like I say, I don't think it's an entirely healthy dynamic, and this is why experiment is so good when it's working properly, because experiment is the thing that it doesn't matter whether you're the whatever named distinguished professor of be a big shot physics at big shot university. Experiment just comes along and says your theory's wrong.
Now, before I move to the closing remarks or closing questions, I want to ask, what is the role for multiple time dimensions in physics?
Okay, so I'll go first.
Sure.
Okay, so there are various questions that I think are fair to formulate. So these include, like, why do we just experience one time dimension? Why does time run forward? Why are the equations of quantum mechanics what they are? Why the Schrödinger equation is what it is. That I think it's fair to say that even on the kind of if you're doing things like string theory, things like profound theories that we know of, these are not answered questions. In the same way you say, why are the equations of quantum mechanics what they are? Ultimately, I think you're just going to come back and say, well, this is what they are. So multiple time dimensions, what role are they? None, as far as I'm aware, but I'm also aware that this is not a very studied. Why do conscious brains? Why do we perceive time moving forward? Well-defined question, but also one that I think we do not really, not really study, and for good or ill, do not spend time thinking about.
Yeah, maybe just to say something related to what I have been thinking about. I mean, so in some sense, a lot of what I have been thinking about has been the relationship between the Euclidean signature and the Minkowski signature theories, which in some sense you can think of, it's the difference between having 0 time dimensions, just 4 space dimensions, and 1 time dimension. And anyway, I think there's a lot of amazing mathematical structure there. Just thinking about 4 dimensions, about this relation between 0 time and 1 time. The thing, and how this works out with spinors and twistors and everything. The one thing is always that kind of bothers me a little bit that I still don't know what to think about is that if you look at the possibilities in 4 dimensions, because you have your choice between what's, in the metric signature, what's positive, what's negative. But you basically got 3 possibilities. You basically got kind of 0 time dimension, so all 4 positive or all 4 negative, and you've got, which is where things are kind of nice mathematically, or you've got 1 time dimension, which is 1 positive or 1 negative. And that seems to be where we live, and that's Minkowski saves time. But there's also this possibility of 2 positives and two negatives, to have this split signature of signature 2 and in 4 dimensions. And that in some sense, the whole story about spinors and reality and everything actually works most nicely in that story. So everything I'm thinking about, there's clearly a story happening over there in this split signature. But as far as I know, it has nothing to do with the real world. And again, it's this problem of, if you're purely thinking about mathematical beauty, I'm very tempted to go think about that 2 signature case. But I just can't see any possible conceivable relation to any question about the real world that I know about. And someday somebody may tell me one. But anyway, that's the only way this topic has come up in my own thinking.
There's something I'd just like to put in, which I kind of wanted to say. It's about the kind of relation between hype and then ultimate intellectual substance. I mean, it's, even if there is some hype-ridden press release about something that isn't a kind of that isn't really very, very substantial, that doesn't take away from the existence of the actual subject. The actual is an intellectual, coherent thing. The existence of things. Peter was referring earlier, I think we're both completely in agreement about, for example, like mirror symmetry. There are lots of these things which are just there, and they're correct, and they're lasting, and they're extremely deep. I mean, areas of mathematics, for example, there are areas which, for example, like finite group theory is one of these areas where at one point there was a lot of work, and then I think the subject basically was exhausted because all finite groups were classified. And that doesn't mean the fact that there aren't lots of new results in finite group theory is not a criticism of the kind of the intellectual value or validity of that. It's just that sometimes you find some things out which are really deep and profound, and you find them out, and they're true, and they're still just as intellectually deep and profound. So, I mean, I am very strong in my defense of the intellectual value and long-lasting validity of string theory. As you said, I'm much more nuanced about whether everything right now is kind of optimized for an environment that creates maximal progress. But my defense of the underlying theory itself is completely unqualified.
Peter, how much of your criticism towards string theory would be removed if string theory was classified as mathematics and not mathematical physics?
I completely, this is the thing that actually drives me nuts, is when people say that, I see all these people criticizing string theory, saying, that the problem with it's just it's actually mathematics, it's not physics. And that's just, no, it's not mathematics. I mean, mathematics this is not, interesting things that come from string theory, but it's, anyway, the problem is kind of what people mean. Maybe I have my own views, which I've been kind of accused of being kind of semi-mystical, in the sense that I believe that deep physics and deep mathematics are heavily intertwined and are in some sense maybe even will turn out to be the same thing. So it's not, anyway, I don't know how to say this, but maybe I'm going in the wrong direction with this, but the just to say that the thing that I really dislike hearing is saying that, the problem with string theory is that it's mathematics, it belongs in mathematics departments, or and it's just, if you look at something like ADS-CFT, there just isn't any particularly deep mathematics there. That does not belong in a math department. Mathematicians might be able to tell you something, but it's an idea about physics, and it needs to stand as an idea about physics. And it's true of a lot of string theory, and the things. I mean, there's a complicated relation, but this idea that string theory is just mathematics, that's really kind of a wrong way of thinking about it, because it's not. I mean, mathematicians have a very our field has its own structure and its own way of doing it. And this is no mathematician would say that this is true. Oh yes, string theory is just a natural part of math departments. That's really not the way it's the way things are.
I think there's I think there's the cultural, often people start off when they're young and they're good at stuff, but then there is a very big cultural difference between maths and physics. And I think one of the Ed Witten is one of the very few people who's really been able to speak both languages almost like as a native speaker. I think most people are either physicists or they're mathematicians, and there's actually quite a deep cultural difference between the two.
Yeah. No. I think it's been one of the great fascinations of my life to see both communities and there is a kind of, I think, a fascinating relation between the two. They are very different. They have different histories. They have very different ways of thinking about things. But I think they are also in some ways deeply related, and it's a fascinating subject to see the interrelation between the two. But the idea that the problem with string theory is just that it's been improperly categorized and should be mathematics is just wrong-headed.
Well, speaking of mathematicians and physicists, a large portion of this audience are either professors or academic researchers in math and physics, and then another large portion are people who are becoming researchers. So, Joe, what's your advice to young researchers, people entering the field? I'm sure you'd want to skip the existing researchers.
To learn whatever part of the subject you want to learn it properly. So try and avoid the kind of popular science books and learn quantum field theory properly, learn GR properly. Then that gives you the position to make informed intellectual decisions about what you really want to study. And in terms of research, I think try and just to echo famous advice by Weinberg, try and be in areas that are messy rather than areas that are clean.
Peter.
Well, I mean, the one category of student I often get to meet and talk to are people who are interested in both math and physics, and I don't. And the standard kind of advice I give them is at least in the U.S., the U.S. job situation that I'm most familiar with. If you kind of can't decide between the two and you like doing both, you probably should go to graduate school and try to have a career in mathematics. You're going to do it's a lot easier environment. The kind of ratio between really, really smart people and jobs where you can actually think about what you want to think about is much better in mathematics. So that's a little bit of just kind of practical advice. It's very hard, how to. I think it's a very tough situation for students who really, understand very well. They want to. They're in love with the questions about fundamental physics. They want to figure out how to do something with this. How to how to make their way. It is very, very tough. And the situation in getting a PhD in theoretical physics, trying to find a job is quite difficult. I don't know to say that I have really good advice for such people.
It's an extraordinary privilege to be able to think about these areas. And
that's really
the worst thing that can happen is someone has to kind of like quadruple their salary by going and working, leaving the subject and going and working somewhere else. So, yeah.
Yeah, I should say also that seeing what's going on with students these days. I mean, most of them are not. Most of them are kind of very worried about and thinking about what's going on with AI and what's going on their own. It's quite possible that we're going to be, we're on the cusp of these these kinds of research and these kinds of fields changing quite a lot because in some ways driven by AI. If only. Whether or not for intellectual reasons, but if only that's where all the money is coming from, and so, mathematicians are very much. I don't know how much effect this having in physics. Mathematicians are very much starting to debate, the standard ways in which we've done mathematics research in terms of, of writing proofs and checking proofs. Should we start using automated theorem checkers or provers, or what is in some sense, mathematics research looks like it's something that AI might actually really be able to do. It's possible it can do it as well as or better, or it can teach mathematics probably better than the rest of us. So what's going to happen there? So I'm curious if Joe has any. If you see this in physics also, what is the AI going to have an impact on people's careers?
I don't have I mean, I do feel that at undergraduate level, we need to have a very clear, there needs to be a very clear thing as to the traditional, there's an awful lot of calculations you do by hand. Yeah. So it's important to understand how calculations work, but I think one has to kind of revisit all this and think, is this, in the same way we don't use slide rules, we have calculators, and think about, as we're training people for the future, learning how to do complicated integrals by hand, is this the right skill set? Perhaps it is, perhaps it's not. But to think about, in terms of solving problems, whether we need to just kind of, the old methods are still the right ones. But I don't have a clear answer.
And lastly, Joe and Peter, what are you excited about research-wise in the near future? Starting with Joe.
So if I talk about the subject as a whole, myself, so I
think
your
own personal research.
I want to talk about both, because if you're intellectually, you need to talk about both. I think so. The subject as a whole, I think gravitational waves is kind of across the spectrum of fundamental physics. I think is the single most kind of interest. It's like it's 10 years after the birth of optical astronomy in 1620. We're really at the very birth of gravitational wave astronomy, and this is going to be the ability to look at the universe in ways. And this also ties to what I'm excited about myself, which is this question of what was the universe, this period between inflation and Big Bang nucleosynthesis, which could cover 30 orders of magnitude in time, and which is observationally unconstrained. How things, particularly for me, ideas from string theory, things about how the evolution of the universe could have been modified then, what signatures this could lead rise to, and how would we observe this? And then this connects then back to gravitational waves, as these are one of the few ways you can actually reach back directly to such very early times.
Peter, what are you excited about?
Well, I mean, I mentioned very specifically the stuff about this, but maybe there's one to connect it to the larger field. There's some, and again, in my mystical feelings that the best physics and mathematics, deepest physics and mathematics are connected. I mean, perhaps one of the most healthy fields in, if you want to say, kind of fundamental mathematics, has been these ideas about arithmetic geometry that are occurring. So there's our functional equivalent of Edward Witten is Peter Schulze in Germany, who has been kind of revolutionizing that subject, and it's part of. Anyway, so it's a story with a long history. This kind of, how do you think about numbers and arithmetic kind of geometrically, and that and there's in some sense there are these things like spaces whose points are kind of primes, and it's a long and beautiful subject, and it's been making a lot of progress recently. A lot of this goes under the name of this Langlands program. A lot of the questions are really about these deep questions about kind of the symmetries of the integers and of numbers, and there's just been a lot of progress on this, and to my mind, I probably spend much more time. I'm in no sense expert in this field, and I'm kind of fascinated by it. I probably spend more of my time learning about it or trying to learn about it than I should. I should be probably doing things I'm better at, but anyway, I think that's a part of mathematics which is really quite healthy. It's moving forward quite quickly, and these most recent developments go along, kind of bring together these ideas about arithmetic geometry with ideas about what's called geometric Langlands, and which actually have a lot of interesting historical connections to physics. So when Witten and people were thinking a lot in the late 80s about ideas that came out of conformal field theory, that the mathematics that they were developing was taken over by a lot of mathematicians and became this field of geometric Langlands, which is quite fascinating. And we're starting to see, especially through Schulze's work, a kind of a bringing together of these geometric ideas the so-called geometric Langlands, and then this arithmetic geometry ideas, and to bring it in number theory. So it's fascinating to watch. And the thing which kind of fascinates me, and I don't really quite know what to think of, is that in these ideas I've been thinking about physics of twistor theory, there's the notion of a point. As I said, it's you should think about a point as something that's called the twistor P1, and it's a CP1 complex projective one space, which is a sphere, but with opposite points identified in some sense. And that's called the twistor P1. It's one of the fundamental things that shows up when you do twistor theory in physics, but especially if you try to do it in Euclidean signature. But the most kind of thing that's completely amazed me is if you look at the recent work on trying to bring geometric and arithmetic Langlands together, Schultz and others are, finding that, if you look at different arithmetic points, which are primes, you find an interesting structure that's called the Farg-Fontaine curve. But if you take, in some sense take the point off to infinity, and if you look at the real numbers, the analog of the Farg-Fontaine curve is the twistor P1. So this exactly the same mathematical structure that I'm seeing is really, I can really do something if I think of points physically that way. Schultz and others have found that, thinking of their more advanced notions about geometry and how to bring them together with number theory, they're also finding the same twistor P1, the same structure showing up. So it's, I don't know what to make of this other than my deep belief in the mystical connection of everything at the deepest level this is probably some vindication of it, but I don't know. Anyway.
Well, thank you both for spending 2.5 hours on the subject of how do we advance fundamental physics and the state of string theory. Before we leave, why don't you summarize, Joe, what is it that you agree with Peter about, and what is it that you disagree with him on?
I think we disagree on the overall intellectual substance on string theory, and I think we agree in thinking there are some kind of problems in how things are kind of organized and in terms of actually making kind of intellectual progress in fundamental physics at the moment. That's how I see it. Peter can tell me whether he.
Yeah, it's more or less right. Yeah, I think we finally. Our fundamental disagreement is, I think, as we discussed, is more just about trying to see forward what is a promising direction to move forward this, and we just see that question very, very differently, and we see string theory's role in that very differently.
Thank you all again. The books are Not Even Wrong. So that's Peter Woit. That's your book. You also have a book on quantum theory, groups, and representations. Joseph, your books are Why String Theory from 2015 and Origins, The Cosmos in Verse. Those are on screen. All of these are on screen and in the description as well. Thank you so much for spending time here on this subject of fundamental physics.
Okay. Thank you.
All right.
Thank you. Thank you both.
That's it. That's wonderful. Thank you. Thank you all.
Merry Christmas.
Don't go anywhere just yet. Now I have a recap of today's episode brought to you by The Economist. Just as The Economist brings clarity to complex concepts, we're doing the same with our new AI-powered episode recap. Here's a concise summary of the key insights from today's podcast.
All right, let's jump right in. Today, we're taking a deep dive into a couple of episodes of Kurt Jimmengal's Theories of Everything.
Oh, you know those. Those hardcore physics discussions, PhD level stuff.
Exactly. Jimmengal really gets into the weeds with his guests. And he's got a serious math physics background, so he really pushes them.
Yeah, he's known for going deep, like weeks or even months of prep before he even sits down to talk with them.
So today we're looking at two physicists with very different views on string theory.
Yeah, Peter Woit, who's a pretty well-known critic of string theory, and Joseph Conlin, who's actually a big defender of it.
It's a fascinating clash of perspectives. And right off the bat, Jimmengal asks them both to grade string theory.
Like a school grade.
Yeah, it's almost like a playful way to get things started.
I like it. Gets right to the point.
Totally. So Conlin, He gives string theory a big A+.
Wow, high praise.
He's really enthusiastic about its potential, for the long haul. But then White, he just throws down an E-.
Ouch. That's rough.
Right. I mean, that's practically failing the theory completely.
So what creates such a huge divide between them?
Well, that's what makes this deep dive so interesting. It forces us to ask, what happens when these brilliant minds can't even agree on the basics?
It's fundamental, right? What are we even talking about when we say string theory?
Yeah, and that's actually one of the first things they get into. They both kind of agree that string theory has become this fuzzy concept.
Fuzzy how?
Well, White, he points out that a lot of research that gets labeled string theory isn't really about, quantized strings anymore.
So it's more than just those tiny vibrating strings they talk about.
Right. And Conlin even says that sometimes string theory is just a way to describe what a certain group of physicists are working on.
So not even a theory, more like a community.
Yeah, something like that. And this is where it gets really tricky, because if we're trying to evaluate string theory, but we don't even know exactly what it is.
It becomes really hard to judge, right? How do you grade something that's constantly changing?
Exactly. And this isn't just an academic problem, it's a fundamental issue in physics, especially when you don't have any direct experimental evidence.
You're talking about, how do you know if a theory is right if you can't test it in the lab?
Right. And that leads them into this really interesting discussion about AdS-CFT correspondence, which is this big area of research in string theory.
Now, AdS-CFT, that's something I've heard a little about. It's about a connection between different dimensions, right?
Yeah, like a duality between a theory of gravity in a higher dimensional space and a quantum field theory in a lower dimensional one. But White argues that this focus on AdS-CFT is kind of leading physicists down a rabbit hole.
A rabbit hole? How so?
Well, he says they're getting too caught up in these toy models. They're mathematically interesting, but they might not have anything to do with our real universe.
So it's they're playing with theoretical Legos, but not building anything real.
Exactly. And he even brings up this recent paper by Ed Witten.
Witten, he's like a rock star in the physics world.
Right. But White sees this paper as evidence that even the top minds in the field are getting lost in these abstract, low-dimensional models. Even Witten's getting sucked in.
Okay, so one guy says AdS-CFT is leading physicists astray, but what does the other guy say?
Well, Colin, he comes back swinging. He defends AdS-CFT, calls it a profound discovery. He argues that even if it doesn't directly describe our universe, it's still valuable for understanding fundamental physics.
Interesting. So even though they disagree about AdS-CFT, they both have strong opinions about it.
Oh yeah, for sure. But here's where things get a little surprising. They both actually agree that there's too much hype around string theory.
Too much hype?
Yeah, all these big claims about how it's going to revolutionize physics. And Conlin thinks all this hype is actually hurting public trust in science.
I could see that. It makes it seem like physicists are all talk and no action.
Right. And White, he goes even further. He sees the hype as a symptom of a lack of honesty in the field.
Ooh, that's a strong statement.
Yeah, he even quotes Bob Dylan. He says, "To live outside the law, you must be honest."
I wonder what he means by that. What's the law in theoretical physics?
It's a great question. I think he's getting at this idea that when you're working in a field where it's hard to get experimental proof, it's even more important to be intellectually honest with yourself.
To admit when you're wrong, to question your own assumptions, that kind of thing.
Exactly. And that's what makes this conversation so compelling. It's not just about string theory. It's about how we do science, how we evaluate ideas when we can't rely on experiments to tell us what's right or wrong.
Right. It raises those big philosophical questions about the nature of truth and knowledge.
And then Conlin throws in this really interesting twist. He argues that string theory can make testable predictions.
Wait, really? I thought that was one of the big criticisms, that it wasn't testable.
Yeah, but he says that even without having one single unified solution for string theory, you could still get predictions out of it. And he points to these things called moduli.
Moduli, what are those?
Well, basically they're particles.
Yeah.
But they're weird. They have these super weak interactions, and Colin suggests that they might have dominated the very, very early universe.
Wow, so we're talking way back, before even the cosmic microwave background.
Yeah, even earlier. And he says that these moduli could have left behind traces, signatures that we might be able to detect in cosmological observations.
So fingerprints from the Big Bang.
Exactly. And if we could find those fingerprints, it would be a huge step towards connecting string theory to the real world.
That would be amazing.
Right. And that's why Conlon's so excited about it. He sees it as a way to finally bridge the gap between the abstract mathematics of string theory and the observable universe.
It's like opening a window into the earliest moments of time.
It's mind-blowing, right?
Wow.
And it just shows you how even in the midst of all this disagreement, there's still room for new ideas, new ways of thinking about the universe.
It really challenges our assumptions about how the universe evolved. Like, we think we know the big picture, but maybe these tiny particles hold the key to understanding it all.
Right. It's like we're so focused on the big stuff, the galaxies and the Big Bang, that we might be missing the really important stuff.
Exactly. And that kind of gets to the heart of this whole debate between Voigt and Conlon. Voigt thinks string theory has gone off track, too focused on mathematical beauty instead of experimental testing.
Like, he thinks they're chasing these elegant theories, but they've lost sight of how to actually prove them.
Right. And Conlon actually agrees to some extent. He's worried that physicists are forgetting how to connect their theories to real-world data. He makes this great analogy about muscles, like if you don't use them, they atrophy.
Oh, yeah. He says you can't just think about walking, you have to actually do it.
Exactly. And that's his point. Physicists can't just keep thinking about theories. They have to find ways to test them.
It's like we build these incredible machines, but we don't know how to drive them.
Yeah, and they both see this as a symptom of a bigger problem in physics, this disconnect between the theory and the experiments. They're even critical of how research is done these days, like how everyone's trying to publish in these big journals and chase the latest trends.
So it's like a popularity contest instead of a search for truth?
Kinda, yeah. Conlon even says that hiring practices are different in Europe. Maybe they're not so focused on trends over there, which allows for more diverse research.
So maybe there's more freedom to explore different ideas in Europe.
Possibly. And that raises the question, is this pressure to be trendy actually hindering innovation? Like, are we missing out on big discoveries because people are afraid to go against the grain?
That's a good question. What would it take to create a research environment where people are encouraged to take risks and think outside the box?
That's a tough one. But I think Voigt and Conlon would agree that we need to reward truly creative research, even if it doesn't fit the mold.
Speaking of going against the grain, Voigt brings up this idea of tribalism in physics.
Tribalism.
Yeah, like how some physicists agree with his criticisms of string theory, but they won't say so publicly because they're afraid of hurting their careers.
Oh, that's kind of scary. Like, there's this pressure to conform.
Right. And he jokes that even people who support string theory might need to remain anonymous to avoid backlash.
So it's not just about the science, it's about the politics of the field, too.
Exactly. And this kind of division can really get in the way of progress. You know, people get so caught up in defending their own turf that they forget they're all on the same team.
Right. Ultimately, they're all trying to understand the same thing, the universe.
Exactly. But even with all this disagreement, Conlon makes a really important point. He says that just because there's hype or criticisms around a theory doesn't mean there's no substance there.
Like, there might be some good ideas hiding beneath the surface.
Exactly. He uses the example of mirror symmetry, which came out of string theory research, but has had a big impact on mathematics.
So even if string theory itself doesn't pan out, it could still lead to valuable discoveries in other fields.
Right. And it shows you how interconnected knowledge is. You never know where an idea might lead.
It's like following a winding path. You might not end up where you expected, but you'll discover something interesting along the way.
Exactly. And then Jay Mungal asks Voigt this really interesting question. He's like, would you stop criticizing string theory if it was just classified as math and not physics?
Trying to put him on the spot there.
Yeah. And Voigt, he completely rejects that idea. He's adamant that string theory is about physics and it needs to be judged as such.
So for him, it's not just a mathematical game. It's about trying to describe the real world.
Right. He even pushes back against this idea that anything mathematically complex is somehow not physics.
It's like he's saying, don't underestimate the power of math to reveal the secrets of the universe.
Yeah, it makes you wonder if we try to put things in boxes too much, you know,
Yeah.
like physics over here, math over there, when really it's all connected.
Right. Like, these rigid categories can actually hold us back from making real progress. And that kind of brings us back to this big question. How do we judge a theory when we don't have experiments to tell us if it's right or wrong? Especially in these really abstract areas of physics.
It's like we're stuck between these two different ways of doing physics, one that values beautiful math and the other that demands experimental proof.
And that tension is really strong in fundamental physics, where we're dealing with things that are so far removed from our everyday experience.
Right. So maybe we need to rethink what we mean by good physics in those areas where our usual methods don't really apply.
Yeah, maybe we need a new approach, one that combines the elegance of math with the grounding of experimental data.
Because in the end, it's that interplay between theory and experiment that really drives science forward.
And near the end of the conversation, Jamin Gall tries to find some common ground between Voigt and Conlin. He asks them, where do you guys actually agree?
Trying to bridge the gap, huh?
Exactly. And it's interesting because Conlin, he admits that even though he and Voigt have these fundamental disagreements about string theory, they both see problems with how physics research is done.
Like the system itself is holding us back.
That's what they seem to be saying. Conlin even suggests that these structural issues might be a bigger obstacle than their debate about string theory.
And Voigt agrees with that, saying that they both think the current system doesn't really encourage innovation.
So even though they're coming from different perspectives, they can still recognize these shared problems.
Which gives me some hope, you know?
Mm-hmm.
It means that there's potential for them to work together to make things better.
It's like they're saying, hey, we might disagree about the details, but we both want physics to thrive.
And that's really inspiring, because it shows that even in the face of strong disagreement, there's still room for common ground and collaboration.
Because at the end of the day, they're both driven by the same desire to understand the universe.
Right. It's that shared curiosity that unites them, even when their ideas clash.
So as we finish up this deep dive into theoretical physics and the debate about string theory, we're left with a big question. Could string theory still point us towards some deeper truth about nature, even if it doesn't describe our universe in the way we currently think?
Or is it a distraction, like Voigt suggests, leading us away from more concrete, testable ideas? We don't have the answers, but I think what's important is that these conversations are happening.
Right. It's the debate, the questioning that pushes science forward.
Exactly. And I think these episodes of Theories of Everything really highlight the complexity of the questions physicists are wrestling with and the passion they bring to their search for understanding.
It's a reminder that science is a journey, not a destination, and it's the journey that truly matters.
Beautifully put. And on that note, thanks for joining us on this deep dive. We'll see you next time.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Kurt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Kurt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate TOEs, they disagree respectfully about theories, and build as a community our own TOE. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, TOE listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/KurtJMungle and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.